Hi, this is our glider project report by Tano and Lucas Campos. This project involves designing, building, and testing a small hand-thrown glider that fits within a 16 by 16 box. The glider must be constructed with balsa wood but can include additional materials. The goal is to achieve 20 feet of flight distance and includes a process of analyzing requirements, generating design alternatives, and making improvements based on testing. It culminates in a class fly-off and a video report documenting design decisions. For requirements, it mainly falls into four categories. The first category being construction. It must fit within a 16 by 16 square, must be hand thrown, have wings, remain intact during flight, not have remote control systems, and be made from balsa wood. For performance requirements, it must achieve a minimum flight of 20 feet and will be judged on forward distance traveled. For design and testing requirements, it must need at least one design iteration and have longitudinal stability. For reporting requirements, we must record the process in a video report less than 7 minutes. For measures of success, a successful glider will fit in the 16 by 16 box, remain intact in flight, be hand thrown, fly 20 feet, fly with stability, have logical decisions with its design, have an improved design iteration, and culminate in a less than 7-minute report. Ultimately, our alternate design decisions were based on wing shape, dihedral, and tail configuration. For tapered wings, it's easier to construct, reduces drag, and has good lift distribution, but it's less efficient than elliptical wings. For elliptical wings, it's most aerodynamically efficient and has even lift distribution, but it's the most difficult to construct. For dihedral wings, it provides lateral stability, helping the glider stay level during flight. And with no dihedral wings, it maximizes lift and glide efficiency since the wings remain fully horizontal. For tail configuration, it was either between conventional or V-shape. For conventional, it improves stability, and for V-shape, it's slightly less effective at stability, but there's less weight. For sizing, fuselage was chosen to be 12 inches long and 0.5 inches wide. Wings were 16 inches long and 3 inches wide because our sources recommended fuselage to be 75% of wings length, and so we maximized wing length as much as possible in the 16 by 16 box. Horizontal stabilizer was a 5 by 2 rectangle because its area should be 20% of wings, and the vertical stabilizer was a 2.5 by 1 triangle because its area should be 10% of wings. Ultimately, for our first design, we chose to go with the tapered wing, dihedral wings, and conventional tails. For our initial design, we decided to create a scaled-down version of our glider, reducing the size to 3/4 of the original. We used styrofoam and cardboard for the construction materials, but when we tested it, we encountered significant stability issues. It had too much lift, which caused it to fly backwards instead of forward. For our requirements, it did not fly 20 feet, nor was it stable, and needed a design iteration. After observing the issues with our first prototype, we realized that our glider needed to glide more smoothly. It was producing too much lift, which was causing instability. To improve the flight, we needed to reduce the lift and adjust the center of gravity for better balance. Additionally, we needed better aerodynamics to ensure a more controlled and efficient flight path. To improve the flight of our glider, we made several key adjustments. First, we decided to remove the dihedral and reduce the wing's angle of attack to simplify the glide to reduce lift. Next, we added mass to the front of the plane using Play-Doh to improve aerodynamics and shift the center of gravity. Additionally, we moved the wings higher on the fuselage to ensure the center of gravity was positioned right in front of the wings, helping with stability and balance.
So after the design changes, we got to our final design. So we can see the wooden glider, and it's kind of cut off here, but the Play-Doh's here at the front, and then the wing shape 16 inches across, and then it's three here, 3 inches there, and then the 2.5 and 1 inch dot back here. So here's our final glider. This is the day of the test. And then the location of the CG, the center of gravity was located at the front of the wings. It was approximately 1 inch behind the quarter cord. And I thought it was pretty cool. We both thought it was pretty cool because we were actually able to balance the glider on our fingertips. So, like right there where my fingers are, you could hold your fingers out there and the glider just balanced by itself. Calculation of the lift coefficient and the drag coefficient. So glider mass, we got to be 34.2 grams. The wing platform area, 20 inches squared. The wingspan, 16 inches. And then the velocity was calculated by a test flight, which went 55 feet in 4 seconds. So we got that to be 13.75 feet a second or 4.191 meters a second. And we got the coefficient of lift to be 0.0149, and then the coefficient of drag to be 6.025 expanded out to the e to the negative 6. And then here's a video of our
Not bad, not
farm we're
bad.
about to do.
Okay.
So final performance, we were overall extremely satisfied. Our glider well exceeded the minimum distance, and we actually won the competition. So over here on the right side, you can see that our furthest distance went 64 feet, and we can see that over on the bottom we signed our names, Lucas and Tano. So that's pretty cool. Definitely excited about that. And then the iteration that helped the best was definitely adding the Play-Doh to the front. It created stable flight and helped the center of gravity move up, and just overall just help create better flight. Were the requirements met? Yes, the glider fit into the 16 by 16 bounding box. It traveled the 20 feet minimum distance. We made iterations after prototyping, so overall, yes, the requirements were met. Final thoughts. We went into this project only knowing theory of how everything worked, and there's a learning curve, but we conquered it over the course of the project to see how it actually works in practice. We're proud of the work that we put in, and we learned a lot about testing the iterative design process. And for future reference, we would probably use a stronger glue to hold the components together, maybe like Gorilla Glue or something, because we just use hot glue. And then also be more consistent with the strength of throw. And I say that because the harder we threw it, the further it went. And I only realized that after the third throw of the actual test day. And here are references. Thank you.